record. Okay, excellent. All right, so first up, we have Miriam Cabrera-Muller. Oh, also, I'm going to ask you guys to just introduce yourself. You guys have 4 minutes. So Miriam, go for it.
Okay, thank you. So yes, my name is Miriam Cabrera. I'm a postdoc at UBC in Vancouver, and I want to talk about GW Skynet. So I'll go quickly to the next slide, since time is limited.
Oh, no. How do I go to the next slide?
We're not ready for that, apparently.
Wait.
Maybe because you didn't do full screen?
Oh, no. Wait, hold on. Miriam, can you hear me?
Yes, I can hear you.
Okay, this was a bad idea. Hold on.
Okay, that's not counting towards my time, is it?
No, hold on.
Don't worry, I paused the timer, Miriam. You are still got money in the bank.
Okay. I am sorry. Oh, God. No. Okay, share screen. Okay, so we got that. Okay, oh, it works. Yes, excellent. Okay. Miriam, can you see my screen?
Yes,
okay.
But is it just going to scroll down? Okay, I see.
Yes. Is that okay?
Yeah.
All right, cool. Go for it.
So yeah, this is a tool that we have created for multi-messenger astronomy. So we know from LIGO and Virgo that we can do multi-messenger astronomy. We have the great example of GW 170817, which was a binary neutron star. We observed a gravitational wave signal first that lasted for a few minutes in the LIGO Virgo band. And then thanks to electromagnetic emission, we managed to pinpoint the actual host galaxy of the source. And we learned a lot of physics just from this joint observation. So the main ingredients that we need for having a successful follow-up campaign is that we need accurate sky localization so that we can point the telescopes and we don't need too much time to cover the entire region. And also we need the release of candidate information so that the astronomers know that there is a gravitational wave candidate and can follow it up. So we know that with LISA, there are some sources that we expect to have much more accurate sky localizations. There are simulations that show that can be from a few square degrees to a few arc minutes. So it's going to be a bit easier in terms of covering the sky. We also have to, we'll see what the information will be released for LISA sources. Next slide. So the code that we have been developing is aimed at distinguishing just from the sky maps, which are the main information that is released for gravitational wave candidates, if an event is astrophysical or not. And the reason to do this is because it is often difficult, even for the search pipelines, as well as for the humans, to distinguish if a candidate is real or not. We have had cases of gravitational wave candidates that were retracted, but there are also cases that were not retracted. And it was only 1 year later when the final results were published that we learned they were not astrophysical. So this is a convolutional neural network that uses that information that is released by LIGO Virgo, which are and uses the 2D sky map image like the ones that are on the right-hand side and the 3D volume images. And for LIGO Virgo sources, we also need the detector network because it will be important in telling us how accurate the sky location is. If it's too accurate and we only have one detector, then we know it's probably instrumental noise. But they are much more complicated cases. For LISA, we won't need this information because it's just one instrument. But the estimated distance is also important in telling us how accurate the sky localization is, and it helps to determine if a sky map comes from a real event or not. Next slide, please. So we trained and tested this algorithm on simulated data. And then when the results of the LIGO Virgo candidates were released on the GWTC2 catalog, we could test it on the real data. So the GWTC2 catalog has the discoveries between April and October 2019. There are 29 non-retracted and unpublished candidates.
Miriam,
yes,
sorry to
1
interrupt.
minute.
That's your minute, yep.
And from those 29, LIGO Virgo told us 22 were astrophysical and 7 were not. So those had not been retracted. We looked for electromagnetic emission and then they were not real. So GW Skynet predicted that 6 of those were not real and 23 astrophysical. So we got just one of them wrong. But most importantly, we got all the astrophysical events correctly. So our recall in this small set is 100%. Our total accuracy was 96.5% because of this one candidate that we misclassified. And with that, I'll finish. Next slide. So GW Skynet is working well with LIGO Virgo. We can very easily use it for LISA sources as well. We'll just need to prepare a new training set. We might have to change very minor changes in the architecture, and then we'll be ready to go with LISA to help us distinguish which candidates are worth following up. Thank you.
Awesome. Thank you, Miriam. Okay. Next, we have Kristen. All right. Okay, Kristen, you have 4 minutes.
Thanks, John. Hi, I'm Kristen Day, and I wanted to talk about ultra-compact X-ray binaries in globular clusters outside of our own galaxy. So next slide, please. So I really love globular clusters. I think they're really neat places. I like making this analogy of saying they're just like a swarm of bees. I think images of globular cluster can give you this impression that the stars are just static, but they're not. And just like bees, there's, hundreds of thousands of them all moving around each other. And because of this, they can form all kinds of crazy X-ray binaries, including ultra-compact X-ray binaries. Next slide, please. So we do know that some galactic globular clusters are home to ultra-compact X-ray binaries, but unfortunately, we only have about 150 globular clusters in our galaxy. So that means that if we really want to understand what's going on with like populations of globular cluster ultra-compact X-ray binaries and like how do they form or behave, or like how many different kinds of systems are there, for LISA, we would like to find more and characterize them. So luckily for us, there are tens of thousands of clusters outside of our galaxy. And even though it's a lot harder to study stuff outside of our own galaxy, we do have one candidate ultra-compact X-ray binary in a globular cluster in NGC 4472. So I wanted to kind of compare and contrast to 47 TUC-X9. Next slide, please. Thanks, John. And just kind of show how we can, use what we know about both of these sources to study the physics of and look for more of these sources. So in the interest of time, I'm not going to go through everything that's similar about these sources, but you can see they have a lot in common in a lot of different wavelengths. And as I like to say, the only difference between these two sources is about 6 order of magnitude in X-rays, but who's counting? But that's actually useful. So next slide, please. So there's this theoretical plot from Van Hoften et al. 2012, which is one of my favorite, I would say, top 10 papers ever. So it talks about like theoretical predictions of formation of ultra-compact X-ray binaries, and has this relationship between the mass transfer rate and the orbital period. So we know that 47 TUC-X9 has a lower mass transfer rate and a 30-minute measured orbital period. And if we use this theoretical predictions to extrapolate where RZ2109 should be, with its much higher mass transfer rate, that puts it at about a 5-minute orbital period. Now, because it has such a high mass transfer rate, the physics of the system is totally different and is actually producing super Eddington outflows and optical emission, which is something we can search for with optical telescopes. Next slide, please. So I don't want to spend too much time on this. This is one of my favorite figures I've ever made, but this is a long-term monitoring and optical study we've done of the source. And because we've spent so much time understanding this really unique source with its really unique optical spectrum, we are very certain that like this really is an ultra-compact X-ray binary, and there's nothing extra to the system that's tricking us. And so because we're so confident in the source, we can now use what we know about the source to search for more. So if you can go to my last slide, please.
Yeah, just under a minute, Kristen.
Okay. I did it. So the question is, how do we find more of these dang things, right? Because, extragalactic astronomy is really tricky and full of bad data, unfortunately. But as it turns out, there is a ton of data out there on a ton of globular clusters that nobody has looked at. So what we can do, kind of the game plan, is we can look for more and more and more globular clusters, look at their X-ray data, find more ULXs in globular clusters, and then understand what's going on with their physics and what's going on in the optical, so we can figure out, are these just weird X-ray binaries? Could they be ultra-compacts or something else? That's all.
Excellent. Thank you so much, Kristen. We are on time and we may even have some time for a couple questions at the end. All right, so next up we have Evan. Evan, you have 4 minutes. Go for it whenever you're ready.
Hello, everyone. My name is Evan Goetz. I'm a research associate at the University of British Columbia, and I'm going to talk to you a little bit about applying LIGO-Virgo continuous wave data analysis methods to LISA data. Can you go to my next slide? So I'm by no means the first one to think about this, but I have a long history of continuous wave data analysis in LIGO and Virgo. In the data that LIGO-Virgo looks at, especially for continuous wave sources, is noise dominated. These continuous wave sources, the expected primary source is a non-axisymmetric rapidly rotating neutron star. And so it's basically a quasi-monochromatic signal. LIGO-Virgo compact binary coalescence data analyses techniques generally rely on matched filtering for a transient signal. There's a waveform template bank that is matched against the data, and candidates are extracted as the data is analyzed in near real time. In contrast, continuous wave data analysis utilizes more complex techniques only in very specialized cases where you have a known pulsar with good timing solution. Can you do a match filter technique? Otherwise, you have to do suboptimal techniques. And you also have to accumulate a signal for a very long time because the signal is weak compared against the data. So this type of signal, this rapidly rotating neutron star, is somewhat analogous actually to certain classes of LISA sources where they may be quasi-monochromatic sources. We've heard about the galactic white dwarf population, but also some of the slightly less massive binaries. They will exist in the LISA band for weeks to months to years. So depending on the time scale that you look at, these may be interesting sources to observe and to they look quasi-monochromatic. Next slide, please. So in LIGO-Virgo, when we do a continuous wave data analysis, we have a certain set of parameters that are we characterize the signal. So I've put on here this vector that describes the parameters that are searched for in a isolated neutron star. We have the sky location, the frequency of the source, the frequency evolution, which is slow compared to the observation time, the amplitude of gravitation waves, the orientation parameters, and some initial phase. As I mentioned, we have to do long observation times because the expected signal is noise dominated. And the match filter analysis technique really only works for pulsars with a timing solution. However, these techniques can be expanded. Markov chain Monte Carlo techniques for parameter estimation could be expanded to LISA sources, as well as the techniques that have to search for unknown parameters. They could also be utilized to search for unknown sources in LISA that haven't been characterized electromagnetically.
Evan, that's your minute.
Okay, thank you. Next slide, please. So just very quickly, there's a certain overlap in the qualitatively between LIGO-Virgo CW analyses and LISA analyses. And so the sort of parameters that one would search for in a compact binary search in LISA might be slightly different, but they're nevertheless sort of the same set of type of parameters. There may be a few more depending on if the spins of the sources in the system are significant and they couple to the signal. But the CW search techniques, as I mentioned, could be useful for this low SNR regime or obscured signals, potentially even to search for things in this confusion limited regime. Next slide, please. So just as the next steps, the idea is to investigate the utility of the LIGO-Virgo analyses and extend the parameter estimation methods and software to the LISA sources, and then to understand under what conditions these types of analyses coming from LIGO-Virgo would be most useful or beneficial for the LISA analyses. Thanks for your attention.
Awesome. Thank you, Evan. All right, some extra slides. All right, next up we have Laura. Laura, you have 4 minutes whenever you're ready.
Thank you. So yeah, I'm Laura. I'm currently a postdoc at the Albert Einstein Institute in Germany, but just a few months ago, I defended my PhD in Canada at Perimeter Institute and the University of Waterloo. So I did most of my research in Canada in the past 4.5 years, as you can see from the photos. And my LISA research is at the intersection of gravitational theory and astrophysics. And one common theme has been the study of environmental and matter effects in LISA gravitational wave sources. So one example of this are binaries, black hole binaries, similar to the LIGO and Virgo binaries, located in very dense environments, such as the AGN accretion disks. These binaries, because of their environment and because they will be orbiting around the supermassive black hole at the center of the AGN, can be affected by a number of effects such as accretion, dynamical friction, or third body effects such as the Doppler and the Shapiro time delays. What we found in our analysis was that for these binaries, LISA will be able to measure realistic values of the density of gas that is being accreted or causing dynamical friction, and will also be able to measure the separation between this binary and the central black hole, and also the mass of the black hole at the center of the AGN. And recently, we've also been trying to extend some of these studies to another LISA source, the extreme mass ratio in spirals. Another LISA source where matter effects are very important are galactic binaries. And in particular, we focused on a subset of galactic binaries where there's a black hole and a white dwarf. And these binaries are less numerous, we expect, in our galaxy and globular clusters, but they're also, they've been an elusive source for astronomers, and so they're a very interesting target for LISA. And what we found in our analysis was that if we model the mass transfer between the white dwarf and the black hole, then we think that LISA will be able to measure all the relevant binary parameters, so the mass of the star, the mass of the black hole, and the luminosity distance. And this is, despite the fact that the signal from these binaries is quasi-monochromatic, so it has very little information in it.
That's it. That's your 1 minute mark.
Yes. So finally, another source where, of course, astrophysics is very important are the massive binaries. And I've recently started looking into these with, in particular, the idea of inferring the population characteristics of these binaries using future LISA observations. And other than doing research for the LISA mission in the more general topic of gravitational physics, I've also been interested in black hole ring down and linear effects in it, and the possibility of having super radiance for electromagnetic waves surrounding a black hole and immersed in a plasma, because the plasma can give photons an effective mass. Thank you.
Excellent. Thank you so much, Laura. And next up, we have Nick. Nick, whenever you're ready, you have 4 minutes.
Okay. So hi, everyone. My name is Nick Vieira, and I'm a master's student at the McGill Space Institute under the supervision of Daryl Haggard and John Runn, which I assume means I get another 30 seconds. But so today I want to talk about our hunt for an electromagnetic counterpart to a LIGO-Virgo source as a sort of case study for what effective EM follow-up can look like and what kind of follow-up is being led by Canadians. So next slide, please. So the source I'm going to be talking about is GW 190814. And this source is really exciting as the first strong high signal to noise candidate neutron star black hole merger with really, really excellent sky localization. And there are a bunch of reasons why you would care about this source. Some of the ones that I care about are, so what do neutron star black hole kilonovae, so that's the UV optical IR transient, look like compared to binary neutron star mergers? Are they redder than our friend GW 17817? And this can have a lot of interesting implications for the R process synthesis of the really heavy elements. If these events are indeed a bit redder than binary neutron star mergers, then they might more robustly synthesize the heaviest of those elements. And then lastly, unsurprisingly, if you see a black hole tear apart a neutron star, that can tell you interesting things about the neutron star equation of state. And so we really could not resist. And so we decided to hunt for the kilonova, specifically counterpart to the source. And so we used the MegaCam instrument on the Canada-France Y telescope to do that. And so I'll go over some of the specifics of that program now. Next slide, please. So as I mentioned, this event was crazy well localized. That's why there's that little box in the bottom right corner telling you where we're now going to zoom in. So next slide, please. So what we're now looking at is exactly where we pointed the Canada-France Y telescope. So each of those colored regions are tiles where we pointed the scope. The G, I, and Z are just names for different filters. For folks who aren't familiar with those filters, the response curves are on the bottom. And our program was to start with the optical filter, so G, and then move on to the I and Z bands. I can talk more about specifics of our observing strategy later on Slack, but in the interest of time, I'll just get to the punchline. So next slide, please. So what you're seeing here is that we did not detect a counterpart, nor did anyone else. But with our observations, we were able to make some really competitive constraints on the event. So on the left, what you're seeing are a few best fit model light curves for the binary neutron star merger from a few years ago, scaled to the distance of this source. And then you're seeing the upper limits that we were able to place with our really, really deep CFHT observations. And you're seeing that we probably would have seen a kilonova like the GW72817 one at this distance, which is an interesting constraint to place. And then on the right, you're seeing the parts of ejecta mass and velocity space. So these are two sort of macroscopic parameters that we care about in these events.
Nick, that's a minute.
Great. And you're seeing parts of parameter space that we're able to rule out. And we're able to rule out pretty confidently a large fraction of the relevant parameter space with our observations. Next slide, please. So again, happy to talk about methods later, but the punchline and hopefully what came through is that with CFHT, we were able to do some really, really constraining and competitive multi-messenger astronomy. And if you look at that author list from a few slides back, this program was really led by Canadians, and I think that's a testament to growing Canadian expertise in multi-messenger astronomy and also excitement in multi-messenger astronomy. And then I think that bodes well given how excited we all are for LISA, which has hopefully come through throughout today and yesterday. And so my last slide, next slide, is just a few questions which I think have started to be answered in the last couple days. But these are the questions that I sort of think about when I think of how are we going to do LISA plus EM follow-up. That's all for me. Thanks.
Excellent. Thank you, Nick. So I'm told that we won't have time for questions, but of course, if you have any questions for the speakers, please feel free to use our Slack space for this meeting. And also do not hesitate to contact the speakers directly, okay? And so our next session will start very soon, and we will exit this breakout room and go to our next session because the next session is not a parallel session, it's a plenary, okay? All right, thank you.